in the system that we called lowercase k. Now let's assume that a point is moving in accordance with the following equations. Remember that in this case we have the coordinates xi, eta, and zeta, and xi will be equal to some constant velocity omega xi times the time tau, because in this reference frame we have the time tau in the moving frame. Then we have eta equal to omega eta tau, and then we have zeta equal to 0. So this point is moving along the xi eta plane. And as I said, omega xi and omega eta denote constants. The system lowercase k is moving along the axis of x of the system uppercase k. So we have the system lowercase k and the system uppercase k. And as I said, the system lowercase k is moving along the x-axis with velocity v. In previous videos, we have already seen that. So if you didn't check them, please go back and take a look, and then come back here if you want to understand this starting point better. Now we want to find the motion of the point relatively to the system uppercase k. And we can do so by considering the Lorentz transformations written like this: t equal to beta times tau plus v over c squared xi, and remember that beta is equal to 1 over the square root of 1 minus v squared over c squared. Then we have x equal to beta times xi plus v tau. Then we have y equal to eta, and then we have z equal to zeta. And we simply have to substitute these expressions here into these equations in order to find how the point is moving with respect to the system uppercase k. So if we substitute, we get x equal to beta tau times omega xi plus v, t equal to beta tau times 1 plus v omega xi over c squared. Then we have y equal to omega eta tau, and then we have z equal to 0. Now from these first two equations, we get x equal to omega xi plus v divided by 1 plus v omega xi c squared times t. And also we get y equal to omega eta t divided by beta 1 plus v omega xi over c squared, which is equal to square root of 1 minus v squared over c squared divided by 1 plus v omega xi over c squared times omega eta t. Now the law of the parallelogram is still valid, just like in classical mechanics, if the velocity or the speed of light is much larger than v and omega xi, because in that case this ratio here will give us approximately 1, so y will be approximately equal to omega eta times t, and the denominator here will be close to 1, and therefore we are left with omega xi plus v times t, like that. And in that case, that is exactly the law of the parallelogram, where the velocities can be simply compounded together by summing. Now we set the following equalities. We have capital V squared, this is a definition, capital V squared is equal to dx over dt squared plus dy over dt squared, and capital V is simply the velocity of the point with respect to the system uppercase K. And this is what we want to find. We want to find capital V. Then we define omega squared as omega xi squared plus omega eta squared, where omega is the magnitude of the velocity of the point with respect to the lowercase k system. And then we define an angle A, which is the inverse tangent of omega eta over omega xi. And if we make a sketch here, we have the direction of xi, which contains omega xi. Then we have the direction of eta, which contains omega eta, and somewhere here we have omega, and this angle is A. And along omega xi, since xi is also parallel to the direction of x, we have V. So A is the angle between V and omega. So if we want to find capital V squared, we simply have to take these derivatives from the Lorentz transformations. They are very easy to take, and we get capital V squared equal to omega xi plus V squared divided by 1 plus V omega xi over c squared plus 1 minus V squared over c squared divided by 1 plus V omega xi over c squared times omega eta squared. And we can also consider the following equations. Omega eta is equal to the magnitude of omega times the sine of the angle A. That's easy to see from this sketch. And we have omega xi equal to omega times the cosine of A. So if we substitute these relations here, we can rewrite capital V squared equal to omega squared cos squared A plus V squared plus 2 omega V cosine A plus 1 minus V squared over c squared omega squared sine squared A divided by 1 plus V omega over c squared cos A squared. Now we can put this term together with this one multiplying this one, and we get V equal to the square root of omega squared plus V squared plus 2V omega cos A minus V squared omega squared over c squared sine squared A, and we divide by 1 plus V omega over c squared cosine A. Now, if the angle between V and omega is 0, meaning that V is parallel to omega, capital V can also be written like this. You can see here that this term will give rise to omega plus V squared, whereas this term here will be 0 because sine of A is 0 in that case. So we have omega plus V divided by 1 plus V omega over c squared. It follows from this equation that from a composition of two velocities which are less than the speed of light c, there always results a velocity that's less than c. For example, if we consider, to show this, if we consider v equal to c minus k, where k is a positive constant and it is less than c, and similarly we consider omega equal to c minus lambda, or lambda is a positive quantity but still less than c, and if we substitute these two expressions there, we can easily write capital V equal to 2c minus k minus lambda divided by 2c minus k minus lambda plus k lambda over c times c. And if you check, this ratio here is less than 1. So this means that this is less than c. So that's easy to check, right? And also, if one of the two velocities here, omega or v, is equal to c, you can check that this composition will still give us something that is not greater than c. So let's assume, for example, that omega is equal to c. We get c plus v divided by 1 plus, here we get vc over c squared, which is c plus v over c squared plus vc over c squared. We can cancel c, and we get c plus v over c plus v times c, which is equal to c. So even if one of them is equal to c, the composition will give us something that is equal to the speed of light, which is correct, because if omega is equal to c, it means that that point is moving with the speed of light. And that point should also move with the speed of light with respect to the other system, in this case to the system uppercase k.